still gonna freaking fail the class, and it's still gonna hurt against me, even though it's just causing me all this angst. Anyway, you have more important things to work on. You have your own angst, which encompasses basically this problem right here.
What problem is this?
Right? Problem 51 from chapter 23.
Which of the 6 review is this?
The first
This
one.
is the first one. We're already struggling.
Have you tried to do it?
No, I haven't done anything yet.
This is a level 3, by the way.
Your honesty is overwhelming.
You know, one day you're actually gonna come to class prepared, I'm really surprised.
He shocked the hell out of me after his midterm.
But
Or I shocked the hell out of myself after my midterm.
that's the one, I can't say anything bad, you surprisingly.
What I do is I just binge study right before the test, and it'll stick with me for a couple of hours. But until that, I'm clueless.
That's the second part.
Hey, what if we had a non-conducting spherical shell that had a radius 2 centimeters and had a radius 2.4 centimeters? And within its thickness, the positive volume charge density, rho equals A over R, where A is a constant and R is the distance from the center of the circle. So, rho equals A over R. R sub A is 2.0 centimeters. R sub B is 2.5 or 3. No, odd 2.4. Odd 2.4.
There's more pictures of each question.
There's a point in the middle which has a 45 femtocoulombs. What's femto?
-15.
Minus 15.
How do you know that?
Because I looked it up.
No.
Times already.
Milli, micro, nano, pico, femto. Right? Atto. Okay. What value should A have if the electric field in the shell is to be uniform? So I'm going to draw a big picture. Big picture. Lots of colors. R sub A. R sub B. R. Point charge. And since the density decreases with radial distance, we want to indicate that with a lot of plus signs here and fewer plus signs the further we go out. Maybe something like that.
The dotted line's the Gaussian surface, right?
The dashed line is the Gaussian surface, yeah.
So
You
how
can call
come-
that RGS if you like, or RS.
So why did we choose to have that in between the two surfaces?
Because we know where we're headed. We don't know until we know where we're headed. But I know where we're headed, so I've chosen it, right? We need to know the electric field inside. We want it to be a constant. In order to get the electric field inside there to be a constant, we need to measure it. And you're only going to get the electric field at the point you measure by putting the Gaussian surface at the point you measure. Any point in here will do because it's all going to be the same. Now we're going to illustrate that with a graph before we go on to the math to make sure we're understanding it. So that's a perfect question to ask. Why'd you choose the middle? Because it's the point I need to know where the E is, because that's all I'm given. I'm not given the value of E. I'm given that E is uniform throughout this. So the Gaussian surface has to be in here. It could be at RA, it could be at RB, or it could be some arbitrary distance R between RA and RB. That will give me the E in that region, which will allow me then to solve for this constant. That's the plan. Yes?
You said the pluses are most towards the middle and...
Yes, more dense and then less dense as it goes out because the density with the constant keeps decreasing with radius.
Alright, sweet.
Yes, quote.
So, do we have to draw a graph on the test?
Yeah.
I would. Unless you're going to use about 3 paragraphs to explain all the stuff that the graph cuts down to 2 sentences.
I do that anyways.
You can do that.
I do both.
It's up to you, right? So, we're gonna need to prove it, because it's the first question on the test. We're gonna need to prove what E of a point charge, but we already know it's gonna be KQ over R squared, because that's E for a point charge. So we know that if we graph E as a function of R, we're concerned about a couple of points. We're concerned about RA, we're concerned about RB, right? The inner and outer radius of that shell. In this part of the graph, for R less than RA, this is point only. Because if my Gaussian surface were here, to answer your question, Elena, if my Gaussian surface were here, the only charge enclosed would be the point. Right? Once I hit surface RA, then I start including more charge, and there's another contributor. But I'm indicating my knowledge of that by saying point only in this region. That's the only contributor to the electric field. If that's not enough words for you, write down something more complete to let you know this, because it makes sense to you now because you're smart. When you see this 18-page diatribe when you're back, you're going to say, where the hell did that come from? Right? So, point only until R, because that's what Gauss's law says. Only the charge enclosed goes into factoring the E. So I can draw that. And I know that's going to be proportional to 1 over R squared. So this graph represents the E of the point. Why didn't I get rid of it in here? What would have caused it to drop to 0 here? If it were what type of material? A conductor and shielding. But what does it tell us the material is made of? Non-conducting, right? So if you want to, you can say non-conducting implies no shielding. That will help you understand what's to come. Okay? I'm gonna shut this sucker off because we're done with him. Road space. It's all up here. It's all up there. It's way down. It's exciting. Oh, get up there. What's up with you? Monday morning? Oh, darn it.
You're struggling
I
today.
am. I'm that student this morning, went for my whole day. Any questions about this?
Yes.
Yes.
So, it's because it's not zero, that's why it's non-conducting.
Because it's not,
Zero.
because that shell is a non-conducting shell. That was given information.
Oh, and then that's why the graph.
And that's why this guy doesn't drop to 0. But he's not the only contributor, right? At this region, it's point plus shell. Because we've started to enter in the shell, right? And we're given that in this region, we want E is uniform, which means that's a constant. The only way to have it be uniform throughout that structure, that means E net at that position must be a constant.
Why do you know constant?
Because we're told we want to solve for A if the E is uniform inside the shell. That must mean that the contribution of the shell must work in such a way that everything cancels but this portion of it, right? So it should be symmetric. Because for every point above, it subtracts from the point below, leaving it equal. I didn't make that very uniform, right? Now, of course, it's not quite like that because as this guy drops, as this guy tries to bring the value down, this guy brings it back up. As this guy tries to bring the value down more, this guy brings it back up, so it always stays the same. Imagine that is symmetrically drawn around that line. Okay? It's hard to draw everything symmetrically. That is the requirement or the consequence of this being uniform. This guy's not uniform, right? In this region, the shell and the point act together to give its net field, which we want to be uniform. That's what we want, right? The point's not doing its part. So the shell has to make up the difference that the point is losing. Now when we leave, bam, it all of a sudden is going to drop down. It's now going to have a net which continues at this point. Because the shell theorem will kick in, right? This is still point plus shell. But it's no longer uniform. Is it? Because now we're outside the shell, we treat it like a point. So this will go 1 over r squared again. Just a different value than the point alone, right? Because you've got the shell to contribute in the same manner. It's a positively charged shell. This is frankly the biggest part of the problem. After this point, it turns into a math problem. Figuring out the physics of the situation is the hardest part. Now, those of you who have seen the solution in the office hour 20 minutes ago might disagree, but what I'm telling you is this is the hardest part. So this is where you have to completely understand what's going on. There's a lot that happened up here to make this go the way it's going. And it will make perfect sense to you now because I'm explaining it to you and you're smart. And you look back at it later and you say, why did this go to there and this go to here? Ask me any questions that might pop up. Yes, thank you very much.
So if it had been a conductor instead of an insulator, what would that graph end up looking like?
Do you have a guess? I'll tell you what it looks like. It's a great question. What would the graph look like? This part wouldn't change, and this part wouldn't change. But because of shielding, the electric field just disappears. This part would still be a constant, but that constant would be 0. Okay. And then it would jump back out here. So it would lose this, only contributor, and then it would take over here. Yes?
So the E net, is that from just adding the E shell to the E point?
What we're saying is E net is always whatever contributes to that location. For this region, the E net will be the point only. From this region on out, the E net is the point plus the shell. But only in the region of the shell is that E net a constant.
So shouldn't the shell be coming from the axis? Why is it? Because if you added that blue to that red, the E net would be much higher.
Oh, you're right, sorry. You're right, it goes the other way. My apologies. You're right, I drew that picture incorrectly. This is not subtracting from that. You're right. If I add this to this, it would be higher.
It's super high.
So the value is, well, it is, I'm sorry, the value is higher. I drew it wrong. The net value is up here. Right. Because this guy's contribution gets added to this guy's. How does that work? As this guy drops, he keeps him constant. That's got to be constant at that value. You're right, I drew that
Yeah,
picture
that's
wrong.
what's confusing. It's just like those two added do not make that E net.
So this guy has to add just a pinch.
So couldn't we just move that shell down to the axis? And that should
Oh,
be-
that's right, it is, thank you. That's right, it belongs down here. The net effect is up there, thank you.
Yeah.
It goes like that. To some point
The
here.
exact same thing, just coming from the axis.
Like that, yeah, sorry, that's E shell, my apologies, thank you. That's E shell.
Let's just go ahead and move the rest together.
That makes sense. Okay. Because E shell has to start at 0, or close to 0, to matter with this guy. And then as this guy drops, this guy goes up by the same amount this guy drops. That's what I meant to do, thank you. And this guy adds this much where this guy loses that much. There we go, thank you.
We're going into the on field for
So
the.
does that E of the shell still contribute to that same constant?
Yes, we have to add them up. It's like he's saying, the red is contributing this much, so the blue only contributes a little. It's got to continue at this point, right? Now, as the red keeps contributing less, the blue has to contribute more.
So that will add them together to make the.
Yes, thank you.
Makes a lot more sense.
It had the right shape, just the wrong location. Starting at 0. Okay, perfect. Okay? Yes.
So the E shell adds, the shell adds E because it has captured some electrons or
No,
protons
no, no.
from the cube?
It is a positive distribution of charge given by this equation.
Oh, okay.
The shell is like.
The shell doesn't exist until this point. Now all of a sudden, it's got charge on it given by that formula. The density decreases with distance. So it has a certain amount of density here, and the density is inversely proportional to the radius, so it keeps getting weaker and weaker. I've indicated that by drawing fewer plus and plus signs like that. Good. Any other questions? Good.
So we're gonna do the T chart now?
Now we're ready for the T. And we start with superposition, right?
Favorite.
And we come back to